Today we're going to start chapter 8, friction. So far we're talking about different methods to calculate for the forces, including how the supporting joint is going to react to the external forces, how the material, how the forces is going to look like within a material. Most likely it's cantilever beam. However, in most of our cases, when we're dealing with forces, we have frictions between two contact surfaces. For instance, if you try to push this box towards to this directions, a lot of time you need, if this one doesn't have any friction, you should use no force to push this thing. However, because we have friction between the surface of the box and the surface of the ground, so when you start to push, you will need to apply some force, and most likely the force you require to move this thing is going to be its coefficient of friction, and this is normal force. So when you draw the free body diagram of this object, what you're going to have is, of course, you've got your pushing force over here. What do I have over here? The gravity or the weight. And obviously, this box is not moving up and down, which means we have what? Normal force. That is exactly the same as the amount of weight, so it's not moving up and down. Other than that, because based on Newton's first law, if you apply a force to something, what does this going to do? It's going to move horizontally, and it will follow with a specific acceleration, because F equals to ma, Newton's second law. However, this is not going to be the case in this kind of scenario, which means we have an friction over here that is going to prevent everything from moving. So based on the formula over here, the friction is going to be written something like this. Okay, so when we are writing down the equation of equilibrium, those two forces, for sure, they're going to be the same. And those two, depending on whether you're pushing it or you're pull it, or you pull it to the other direction, the direction of this force is going to be changed a little bit. Okay, we're going to talk about different scenarios today, but when we are talking about the friction model, there are a few things you would need to do. Friction, actually including two parts. We can say it's static friction, force, or dynamic friction, force. If I have my vertical axis as my friction force, and my horizontal axis is my pushing force, or Okay. What are you going to see? What are you going to see? When you are dealing with something like this, if you apply just a little bit, for instance, if I just provide a little bit force over here, am I going to move the table? Obviously not. But when I start to increase my force, it's not moving either. Only when my my pushing force is greater than a certain amount, it will start to move. Which means if you just apply a little bit force, the friction is going to compensate for the force I apply. So the friction is going to be increased based on how much my pushing force applied to it. Only when my pushing force is greater than certain amount, the object starts to move. Everybody with me, right? Everybody agree with that, right? So it means that the friction is always the same as your pushing force, as my pushing force, because only when those two forces are the same, the object will not move. It means that if you say your friction is always something like this, that's also wrong. Because if you do the normal force, for instance, this one is what? Let's say this table over here is 20 kilograms. Multiplied by 9.81, that is going to be 196 Newton. Pull downwards, or the normal force is going to be like this. Let's say the coefficient over here is just 0.2. When you multiply this number with this one, how much we actually have? We almost have 40 Newton. When I'm not doing anything, if you assume the friction is always 40 Newton, what happens if this one is 0? What happens? Will this thing start to move? Right? If you don't have anything over here and you say your friction is 40 Newton, and this force is not balanced over here, or the force on the horizontal axis is not 0, which means if I'm not doing anything, the friction should move towards to this direction. Is that going to happen? Obviously not. So the friction over here should be what? If I don't have this, it should be 0. Everybody agree? So it also implies this force is changing. The equation I put over here is the maximum force you should apply without moving it. So the force P and mu s n, you add them together, it becomes 0. If your P is smaller than this number, your object won't move. Okay? So it's also something like this. Even though you increase your push or pulling force, when it's increasing, the friction is always the same. Only when you achieve certain amount, you will start to move. When you start to move, the friction becomes a constant. This number over here at this point is mu s n, the friction coefficient, but actually I should call it static coefficient of friction. Normally I use mu s to represent this coefficient, but when it overcomes this point, the friction is going to drop. Depending on what kind of material you're using, the dropping level is going to be different. So when you are when your object starts moving, then you use different coefficient. Normally we use mu k. Mu k means dynamic coefficient of friction. It is a constant. When it starts moving, when the object starts to move, the coefficient becomes a constant. Okay, and it will become mu k multiplied by n as a resistant force, depending on which direction your object is moving. is always opposite direction. Friction. So sum of rule. You must remember this when you draw your free body diagram. If you fail to do this, your free body diagram is going to be incorrect. Okay? So that is a concept that we're going to adopt in this chapter. Is there anything difficult to understand, or you don't really know what I'm talking about? Any question? No? Okay, if not, then we're going to talk about one of the problems. So, the first example is like this. I have a slope which is 20 degrees. I put a box over here. The block is 50 kilograms. And I apply a force, horizontal force over here. Mu s is 0.4. When you are dealing with this kind of problem, be sure, because a lot of time you are given two numbers, mu s and mu k. Normally, when we are talking about static force, friction force, we use mu s. Don't apply mu k in this kind of problem. And typically, mu s is greater than mu k. So another rule is, if you see the problem is giving you two coefficients, use the greater one. Okay. A 50 kilogram block rests on a 20-degree inclined plane shown. The coefficient of static friction between the block and the plane is mu s equals to 0.4. Determine the maximum horizontal force P that can be applied to the block without causing it to slide. Okay, so we are given two things, or actually four things. Zeta equals to 20 degrees as well. Those three things are given in this problem. We want to find the maximum value of P without moving it. Okay? So the first thing we need to do is what? As usual, free body diagram. So when you draw your free body diagram, it's going to be like this. There are something given over here, P. Okay. Now I have a question to you guys. This is the most common mistake you guys is going to make in the exam, in the homework, and for some reason I don't understand why you guys do this. I simply have no idea. When I drop my notes, which direction is going to fall? Okay? Mike, can you help me? Get this? Drop it. Which direction is going to fall? Down or fall into the incline? Surface? No. Right? Okay, thank you. I have no idea. When you guys draw the weight over here, I would say 40% of you guys draw your weight like this. The Earth is not going to change the direction of the gravity. Most likely, if you drop everything, well, unless you go to haunted houses, in that case it might be different. But in 99.9% on the Earth, the gravity is what? This direction. Okay, I'm saying this now, and I can almost assure you guys when I'm grading the problem in the exam, at least 20% of you guys is going to draw something like this. I have no idea why you guys do that, because it's not going to change at all. When you have this kind of problem, it's always downward. Yes.
Well, I remember that sometimes I think when you set these up, if you have like an inclined ramp where say it's 20 degrees, you draw your free body diagram and pretend like it's flat on the x-axis.
I'll explain that later.
Okay.
That is sometimes we change our coordinate. Okay? But before I change my coordinate system, you draw your free body diagram, always have your weight point down. There is a reason why we want to change the coefficient, the coordinate, but it doesn't matter how you draw it. It has nothing to do with how you draw your free body diagram. Okay? Before you change your coordinate, you always have something like this. Okay? No, I shouldn't do this. I should point to the center. This one is going to be 50. $491 Newton. Okay? This time, I do need to ask you, since this rests on the incline, what is its normal force is going to look like? Is that going to be vertical up, or is perpendicular to the contact surface? Perpendicular to the contact surface. This is another mistake you guys are going to make. Perpendicular to the contact surface, normal force. Two rules. Rule one, the weight or the gravity is always vertical downward. It has nothing to do with the degree of your inclined surface. Okay, it doesn't matter this 20 degree, 30 degree, 40 degree, or 100 degree. It's always downward. Okay. Second rule, the normal force is always existing, and it exists. The normal force is always perpendicular to the contact surfaces. No matter what you do, it's always normative. Okay, so that's the reason I have a weight over here downward, and this one is going to be this direction. Okay. Now, my pushing force is toward to my right hand side, which means I try to push this block move upward along the surface. So when I say the moving direction has a tendency to go this direction, what is the friction? What is the direction of the friction is going to look like? Opposite direction, right? So it's going to be, okay, perpendicular to its normal force. Now I'm telling, I'm trying to get in the maximum pushing force over here, which means when I apply this force over here, it's about to move, but it haven't started to move, which means I'm talking about this point. Everybody understand what we're trying to do? Any question? Okay. So we can start to solve the problem now. There are two ways to solve this kind of problem. One is you use regular x, y coordinate. Okay, that is the question you're just asking. So if you deal with something like this, well, you don't have any problem with p and w, but you do have problem with n and mu as n, right? In that case, it will be more difficult to solve because when I say it's not moving, which direction we're talking about is not moving? Well, it actually all directions, but I would like to know this direction because it's easier for us to visualize what's going on. If you try to do something like this, you need to decouple this into x direction and y direction. Even though the angle is given, it's still a little bit tedious to figure out what's going on. Okay, so instead of when you see a problem with an incline, normally I would like to rotate the coordinate system a little bit, so it will be aligned to the friction direction and the normal force. However, in that case, you will need to know what angle the weight and the pushing force is going to be rotated about this coordinate. Obviously, I say 20 degree over here. What is the angle over here? 20 degree. Which is also 20 degree. Yeah. Another mistake you guys is going to make is there is no guarantee. Horizontal is always cosine. Vertical is always sine. It's simply not guaranteed. So if you are using this coordinate system, horizontal x over here, if you try to, let's do the formula directly, then I'll ask you guys whether it should be cosine or it should be sine. So even though I tilt the coordinate system a little bit, actually it's 20 degrees, this is still not move. This is still not going to move at all, right? So which means the total force along x-axis should equals to how much? 0. Okay, that's always the rule. So when I'm doing this, I have P cosine 20 degrees. This one is, well, this is perpendicular to the x direction that I'm talking about, so it's not going to do anything along the x-axis over here, but the weight is going to do some, put some value in this equation. In this case, this is going to be weight sine or cosine, 20 degrees, sine. And in this case, is that going to be the negative side or positive side? Negative. Okay. And we say the friction is always opposite to the pushing force over here. So it's going to be something like this over here. This equation equals to 0. Everybody with me? Is that straightforward? Everybody understand what I'm talking about? Any questions? No? Okay, then we figure out what's going on in y-axis. So over here, of course, I have my normal force. Over here, I have weight and pushing force as well. In this case, my weight is going to be what? Sine or cosine? Cosine. Positive or negative? Anything else? Pushing force? This time, sine or cosine? Sine. Positive or negative? Negative. Equals to what? 0. Okay, so we have two equations. The next thing is we need to plug in all the numbers. So it becomes P cosine 20 degree minus 0.4 n equals to 491 sine 20 degree, and minus P sine 20 degree equals to 191 cosine 20 degree. So based on those two equations, you will conclude P equals to 439 Newton. Okay? This is the maximum. So which means when I have this force over here, this is about to move, but it haven't started to move, which means it's going to be the point over here. Everybody agree? Everybody with me? Now, another question I'll ask. It's not specified in the problem statement. I should put next over here. Now, I have another question for you guys. If I remove this force, is possible this block sliding down? It's likely, right? We cannot do that. We don't really know at this moment because we don't know whether this number is going to be greater than the over here. This one is removed. This one is removed. We don't know whether the normal force is going to be we don't know whether this one is going to be greater than something over here to prevent it from dropping. But there is another problem that's going to ask you, what is the minimum force you're going to apply for P so that this object is not going to slide down. So when we have this kind of problem, the free body diagram needs to be adjusted a little bit so we know what we're going to deal with over here. In this case, the weight is still 491 Newton. The normal force is still perpendicular to the object. The P is still applied to this direction. How about the friction? Since I said it's going to slide down the slope, do I need to change the direction of mu s n over here? This time it's going to in this direction. So what is the direction of the mu s you're going to draw on this free body diagram? This direction, right? Okay. Anybody has problem with this equation? Is that straightforward? You guys understand what I'm trying to do? Okay. In this case, again, you would need to determine the direction of your coordinate. You can use regular coordinate, or you can use tilted coordinate. Normally, I would like to use tilted coordinate in slope problems. Okay. So if this is going to be the case, the two equations are the things you need to deal with. When we say it's going to be when it's on the horizontal axis, we have P cosine 20 degree minus W sine 20 degree plus mu s n equals to 0. Y direction is going to be normal force minus W cosine 20 degree minus P sine 20 degrees equals to 0. Almost identical to the equation over here. Well, it's actually identical. Okay, so you can just plug in the number. The only thing that we change is the sign in front of the friction. The reason is over here we try to push everything uphill. Over here we try to prevent this object sliding downhill. So though this is the only thing, you have different signs between those two scenarios. So that is something you need to pay attention to. Any question? Is that clear? Everybody understand what I'm trying to do? If I give you guys this kind of problem now, can you solve that? Well, not solve that. Can you write down the equation correctly? You sure? Okay, we're going to have a quiz today. Okay, so over here I have P cosine 20 degree minus 0.4 Newton equals to 491 plus sine 20 degree. We have N minus P sine 20 degree equals to 491 cosine 20 degree. So two equations, two unknowns. The N and P are the two unknowns. And this time the P is the minimum force that you try to prevent everything. So if you do that, you're going to find the P is actually negative 15.47 Newton. What does this mean? Is the direction, I assume it's up, is pushing it, correct? Or it's actually, the force actually should be in this direction to drag the thing downwards. Which case we're talking about? This is negative. When I say it's negative, it should be this direction. So it also implies between those two forces, this object is not going to move at all. Means if you apply force, if you try to push everything upward, you need to greater than 439 Newton. This thing can move upward. If you try to have this object moving downwards, you need to pull it, actually physically pull it downwards with this force, so it will start to move. It also implies that if I just put this thing over here without applying any force, is this going to move? Or it will just rest on the slope? It will just rest on the slope because when P equals to 0, it's not going to move. Does that make sense to everybody? Any question? If I give you guys this kind of problem in the exam, you guys know how to solve that? You sure? Okay.
Exactly like that one. It's different numbers, right? Change the angle. Change it to like 25 angle.
I cannot guarantee anything. Okay. There are a lot of different. I know friction is one of the problem. Give you guys headache this semester. How many of you guys think friction is difficult? How many of you think, oh, that's a piece of cake? Okay, somebody raise your hand. Good. Now don't worry, I'm not going to give you guys very challenging. I'll give you guys reasonable problem in the exam. Let's work on another example, then I'm going to move on to different types. I won't be able to finish all the problems in your notes, but I'll post the solutions on the solving procedures online, so you guys can take a look. Even though I didn't explain that in class because I think I have 6 or 5 or 7 problems in your notes, which is very unlikely I can go through all of them. Let's do the second one. So there is a movable bracket shown in the self-locking device. When the load P is placed on the bracket at a point over here, far enough from the axis of the pipe, the bracket will not slide downward. Find the minimum distance at which the force P, this force, equals to 160 pounds, can be applied without closing the bracket. To step if the friction coefficient in all contact points is 0.25. The bracket itself is 20 pounds. The gravity center is located at G. So we are given few things. The pushing force is 160 pounds. So let's start identify what's going on over here. Then we're going to draw a free body diagram. In this case, you do need to think about which point is the supporting parts and which point you need to apply friction coefficient, because not all the contact surfaces has frictions. So those are the things given in the problem statement. The pushing force is 160 pounds, weight is 20 pounds, and the coefficient of friction is 0.25. We want to find the distance of D, where you can apply this force as far as possible. Okay. So I mark A, B, C, D on this bracket. Those points is not shown in your notes. I just make it up. So when you start to apply force over here, based on your common sense everything is based on condition. Which points are going to be contacted with the pipe? B and A. Do we have any contact at C and D? They're about to leave, right? So when we say it's B and A, which means we have normal force at B and at A. It also implies we're going to have friction forces at A and B. Do we need to care the things happening at C and D? No, because they are not contact. Well, they are, you see they are contact structurally, but they are not really providing anything. So supposedly we shouldn't have any force at C and D as normal force. When we do not have normal force, do we have any friction? No. What is the definition? What is the formula we use for friction? Mu multiplied by normal force, right? So when normal force equals to 0, which means how much friction we're going to get at the point 0. With that said, free body diagram. It's going to be a little bit different. So this is at A, this is at B. So when I start doing that, this will be what? Tilt downward, right? Or rotated downward. So the normal force you're going to have at A is going to be NA. The normal force you're going to have is NB over here. And at G, you have weight of 20 pounds. P is going to be 160 pounds. We don't know the distance at this moment. This one, Now, I have a question. What is the direction of friction? We know the magnitude of the friction is going to be mu S N A and mu S N B, but what is the directions? Up or down? Up, because everything is trying to push everything down, so it's going to be trying to prevent everything sliding down, so it's going to be mu S N A, mu S N B. Does that make sense to everybody? Any questions? Okay, then if everybody agree with me, then we will start to solve the problem. How many? Well, this is not on the incline plane, so I'll just use regular XY coordinate. So when I start to write down the equation of equilibrium, how many forces I need to consider in horizontal axis? 2. They are NA and NB, and they are like this, which implies they are equal, right? For y direction, we have negative 20 and negative.
A little bit better why we're using A and B.
Okay. So no, that's actually something I want you guys to know. So when you put a pushing force over here, what is the tendency of this thing to try to move? right?
Yeah.
So when you try to stop this one from rotating, is this one? This is about to pull in this direction, right? So this point A must stop it. Point D has nothing to do with it.
Okay.
So that's the reason I don't use D, because though they are contact, it's about to leave. Because I'm rotating this direction, so it has a tendency to pull them apart. Same here. So when this is rotating in this direction, B at this point try to stop everything from moving to this direction. So this part is what? About to move. So I used A and B instead of C and D. Does that make sense to everybody? There are some kind of those things you need to figure out when you're dealing with the problems. Sometimes it can be a little bit tricky. Okay, so I have two equations over here, and over here mu s is given 0.25. NA and NB are also known numbers. So we can get 0.25 NA plus NB equals to 180 based on the second equation. And we also know NA and NB are equal, so nothing fancy. You can conclude those two forces are 360 pounds. But that is not something we try to solve. What do we try to solve? How far this thing can apply to away from the center over here. That is something we try to do over here. So it also implies that it doesn't matter how far this is applied, as long as this 160 pounds is not going to move, it's going to be the normal force is going to be the same. Okay, because at this moment I don't have the coefficient D included in Fx and Fy, and this guarantees it's not going to move. In order to ensure how far this one can be applied, we can use the moment equation. This time I would like to use B as its moment center. Of course you can use A, but this time I just want to use B. So in this case, I have 20 pounds, 160 pounds, and the friction, normal force, those four terms create moment around point B. You need to consider all of them. So when we're doing this, we're going to have negative 20 multiplied by 3. That is between this point and this point. This 4-inch is G away from the center over here, but B over here is actually 1 inch away from the center of the pipe. So when you consider the moment arm, you need to take this into consideration as well. So it becomes 3 inches over here. And we also have the 160 pounds. The distance or the moment arm is going to be D minus 1. For the two normal force and frictions, they are 360. That is my normal force, and the moment arm over here is 5 inch, and this is going to be counterclockwise, so I have a positive sign over here, and the other one is the friction, which is 0.25 multiplied by 360. The distance between this force and B vertically, or the moment arm, is what? 2 inches. And this force is going to be clockwise moment for the reference center P. So this is going to complete my equation. All of them needs to be equals to 0. If you find they are not equal, it means it starts to rotate. If it's smaller, it means that you don't need to worry about the friction over here because it's always greater to compensate the rotating. But if you put your friction over here, and this is still not equals to 0, it means that you will push your 160-pound force too far away, you're going to break the pipe over here. Or the friction is actually will not be able to stop the rotating. So when you do this, one equation, one unknown, you're going to find your D 10.75 inch away from the center of the pipe. So this completes my calculation over here. Yes?
Why is it D minus 1?
D minus 1 is because my D, I use this one as my moment center. So this is my, but D is actually over here. So it's actually 1 inch shorter than D. Does that make sense to everybody? Okay, let's take a 5 minutes break. Problem. So you've got the cabinet. You need to push that to the location where you want to locate it. So when you start to push it, there are only 2 possible scenarios you're going to, which is going to happen. One is you move this cabinet without any problem, so it's sliding along the floor. You scratch the floor and scolded by your parents. The other scenario you might have is you tilt this thing and push that down. If you're a child, you're in big trouble. But when you start to do that, you always have a tendency, you're going to rotate everything to this direction. Depending on how much force you apply, how high you apply the force, it can be tilted or it can be moved. Everybody agree with me? Is there any third possible scenario? Of course, if you're strong enough, you just lift that and move that. So, but we're not discussing that here. So when you are dealing with that, the P over here has a tendency to rotate the whole thing. So if that's a scenario, when I say start to rotate, which point is going to be the reference center, reference point? In this case, let's say this is A, B, C, D. Which point is you're going to rotate that to that? A, right? So when you have a P over here, you're going to rotate around point P. If your force P is big enough, over here, this is our contact is about to rotate itself, and there is no contact forces over here. So at point A, you're going to apply 2 forces. One is normal force, which prevent everything moving up and down. The other one is you also need to apply friction over here. So that it's not going to move horizontally. So, question is, it's going to slide or it's going to kick? That's going to be the question. How do we determine that? If you use this one as your moment center, how many forces are going to create moments? 1 force or 2 force? 2. Which are they? weight and the pushing force. So the moment arm is going to be H over here, and if the weight is going to be this. If your moment arm over here is greater than this number, what happens? You will start to rotate, which means it's tipping. It's tipping and slide, actually. If this one is greater than this force, it will tip and slide. Everybody with me? Okay, so if this force is greater than this number, is going to tip, is going to slide. If pH is smaller than this number, there are few scenarios. This number is smaller than this moment, than this moment, and your pushing force is smaller than the friction. What happened? Is that going to move or rotate? No, so nothing going to happen. H2. So, based on this, it's not rotating, but based on this, the pushing force is greater than your friction, so it will start to sliding. No matter what you do. It doesn't matter, those two need to be equal or not. Even though this is something like this, it will slide and tip. So no matter what you do, this block is going to tip off. Does that make sense to everybody? When this on slope, it's going to be similar. A 60 kilogram refrigerator having a center of mass G is mounted on 4 casters. The friction coefficient between the locked caster and the floor is 0.5. Determine the magnitude of the horizontal force P required to move the refrigerator when H is 1 meter if caster B are locked or if caster A is locked. So we have two scenarios and we need to calculate how much force we can move the refrigerator without tipping it. So we are given the mass of the refrigerator is what? 60 kilograms. The coefficient between the lock caster and the ground is 0.5. And I say I'm going to apply the pushing force at height equals to 1 meter. Anything else? No. I want to find the pushing force if A lock or B lock. Okay? So let's start. Let's start from the first scenario. A is locked. When I say A is locked, B is unlocked, which means this can rotate freely, which means the friction coefficient is 0. Okay? So the free body diagram for this case, something like this. Now I say A is locked, B is unlocked. So can you tell me where I should place my friction in this free body diagram? Here or here? A. And that is going to be mu S and A. Do you think NA and NB are going to be the same? Depends. Normally it's not going to be the same. Okay. But this is pretty much our free body diagram. So let's start our equations. Since this is not tilted, I will use x and y, regular x and y. So I have negative mu S and A plus P equals to 0. So if P is greater than this value, you will start to move horizontally. And we also have Fy equals to NA plus NB plus minus W equals to 0. From this equation, mu S equals to 0.5, so we can know if P equals to 0.5 and A is about to move. If you just add a little bit to the pushing force, the refrigerator will start to move horizontally. Everybody with me? So the other question we might have is whether it's going to rotate when I apply things over here. Then you will need to know this. I would like to use A as my rotation moment center. I would make it, try to see whether it becomes 0. So if we do this, we have the weight. This is 0.8 meters, and the center of the refrigerator should be in the middle. There's a reason I have 0.4 meters over here. Okay, and my P is going to generate another moment clockwise. The only force that is going to prevent everything is MV, which is 0.8 meters away. And since I say this is not rotating, it better equals to 0. If you do this, you're going to find we are talking about 0.4 W equals to negative 0.5 NA, because I can replace this one with this equation over here plus 0.8 MV. So I also know that W equals to NA plus MV, which we can solve NA equals to 407.49 Newton. MV equals to 181.11 Newton. Any question so far? No, I'm sorry. I copied down the wrong one. This is MV. This is MV. Okay, so I know P is 0.5 NA. So P, if P equals to 90.55 Newton, then I'm about to move the refrigerator towards to the right hand side without tipping. Does that make sense to everybody? In another case, E is allowed. The free body diagram is going to be a little bit different. When I say B is locked, the coefficient is going to be here. Okay. You can see, just put down all the required equations, and we start to solve the moment equation to see whether it's going to rotate or it's not going to move. It's going to be NA plus NB minus W equals to 0. Over here, this is going to be P minus USNB equals to 0. Again, in this case, P equals to 0.5. From the first equation. Then in this case, I would like to use B as my moment center and calculate whether it starts rotating based about point B. So when I do this, it's going to be 0.4 W, but this time it's going to be clockwise, and P is multiplied by 1. In this case, it's still clockwise, so it's going to be negative. The other force we have is NA. And that's 0.8 meters away, and it's created clockwise moment, so it's a negative sign in front of it. In this case, it still need to be 0, hopefully. So if we start to solve this thing and keep everything equals to 0, you're going to have NA plus NB equals to W based on this equation. If you do things over here, I know P is 0.5 MB, so I have 0.8 NA plus 0.5 NB equals to 0.4 W from the from the moment equation over here. So over here, it's really straightforward. W is some coefficient, so the only unknown in this equation is NA and NB. So if you solve this one, you don't really need to solve these two equations numerically. You can just do symbolically, and you're going to find NA equals to negative 0.5 weight, and NB equals to 1.5 weight. Okay. So when NA equals to this, everything equals to 0. But we have a problem here. When NA equals to negative 0.5 W, what does that supposed to mean? The direction over here must be downwards. So when it's downwards, obviously this is point contact. The only thing you can do is what? Upward. Can you provide any force downward? No, unless you have a rope, tie this one down to the ground. Otherwise, this is not going to happen. Which also means when NA equals to 0.5 W, the pushing force over here always going to tip the refrigerator off. So the answer over here is impossible. I think it's to push, to move the refrigerator without It also means when you start to push this refrigerator, which caster you should lock, NA or NB? A, right? If you lock A, it's possible for you to move it. If you lock B, the only thing you're going to do is to tip it. It's also reasonable, right? Because if you lock this one, you can see if you use this NB is going to provide some kind of counter force to prevent everything from rotating to the side. If you're doing something like this, it will start to tip over. Okay? Any questions? I can almost ensure you this kind of problem is going to be in the exam. Okay? Okay, so I have two force, a pulley or a belt, and I have a belt around the pulley. So I would like to know what is the friction we're talking about. So let's say this is rotated to this direction, which means which one is bigger? T1 is bigger or T2 is bigger? If the rotating direction is this direction, T2. T2, obviously, right? So, what is the relationship if we start to deal with the friction? Because you can say, I provide force from here, but how much I can actually pull from this side? It's going to be a ratio, depending on the friction coefficient and angle over here. Sometimes you're going to see TH over TL. H means higher power, higher force. L means lower force. Okay, so nothing fancy. You just need to know the coefficient and the angle. But the angle over here, do not use degree. This is radian. So 180 degree equals to how much radian? Pi. Pi over 6. So if you want to convert between radians and angle, it's okay. So if you say this is 30 degree, it becomes you can replace this number with anything you want. Okay, so to be sure, angle if given an angle, you multiply this number with pi over 180, you get in terms of radians. Okay, so be sure you know what we're dealing with over here. This is pretty straightforward. I'm going to give you one example and finish the other example tomorrow to allow you guys to be available to solve the problem. The quiz, I mean. So I have a cable like this. This is wrapped around a fixed shaft more than one complete turn. The force, the object over here is 100 pounds, and the force T is applied to this end, to the free end of the rope at an angle of 30 degrees from the horizontal. Knowing that the coefficient of static friction between the rope and the shaft is 0.2. Determine the range of force which the block will neither raise or lower. So there are two scenarios that we need to deal with. We are given the weight equals to 100 pounds. US equals to 0.2. We are given an angle, let's name this one theta. Theta equals to 30 degrees. Phi range of T. Okay. So the free body diagram is based on the shift. Obviously, there is 100 pounds force. Pull everything down. And my T is over here. This is 30 degrees. And this is of course 60 degrees. This is more than one complete turn, so keep that in mind. Okay, now the first thing we need to determine is the angle, beta. How much I'm actually talking about. I'm not just have a belt like this and have this one as 60 degrees. No, I'm not doing that. What did I do? I wrapped the belt one complete turn, which is how much degree I'm talking about here? One complete turn. 360. And I keep on wrapping on the shaft until the angle becomes 30 degrees over here. So how much more angles I'm actually tight on the shaft? 60, right? Because I keep on wrapping it until this is 60. So it's actually over here 60 degrees plus 60 over here. Everybody with me? Okay. Can I use this directly to this formula over here? No. What do I need to convert? To radians. What do I do? Multiply by what? 180 pi over 180. So in this case, we're going to get 7.33 radians. Does that make sense to everybody? So I'm going to use this angle from now on. But I do have two scenarios. One is I try to raise everything. So it means that this one is going to be moving upwards. When this one is moving upwards, which one is greater? 100 pounds or my T? T is greater. So based on this formula, should I use 100 pound as TL or TH? TL. My mu s equals to 0.2 over here. My beta equals to 7.33 over here. So I just plug in the number over here. Then EH is straightforward. This is actually 4.33. Only when my force is greater than 433 pounds, then I can start to raise things over here, which makes sense, right? When you start to stop something, you just wrap that on a shaft. Then it's kind of difficult for you to move that at all. Only when you provide force large enough, then you can start to push something when you wrap on a shaft, right? If you try to lower it, what's the difference? So in this case, if you try to lower it, which one is greater, T or 100 pounds? 100 pounds. So in this case, 100 pounds is TH or TL?
Yeah.
Good. So it is TH over TL. Or TL. So in order to prevent the 100 pounds to sliding down, you only need to provide 23.1 pounds. So everything is not going to move up, it's not going to move downward. It also means between can you move the 100-pound block over here? You cannot move it at all. It will just remain still. Does that make sense? So in this kind of problem, really, it's really just one formula you need to remember. This one. So, but it's going to be a little bit tricky. You need to identify two things. One is the angle. If it's just something like this, then that will be straightforward for you to figure out. But if I'm telling you it's greater than one complete turn, it is actually 2 or 3 complete turns. This thing over here can be tricky, so be sure you know what you're dealing with. That is one thing. And the other thing is, this is no longer degree. It's in terms of radians. So be sure you're using radians instead of degrees. Okay? Third thing is that you need to identify which direction this is rotating. If it's moving in one direction that your force is providing, it means this force is greater. So be sure you use TH on one side, or if it's lower or it's actually trying to prevent it, then this part becomes TL. So those things are something you need to keep in mind and identify based on the problem statement. Does that make sense to everybody? Question? Okay, I'll let you guys